Okay. All right, we'll go till, I guess we have 45 minutes. But I want to start the first topic, which is just kind of as an application area, which is the problem of flashback. But it also introduces a lot of problems with generally what I would call flame aerodynamics. And you may not be used to seeing those two words together, but the whole idea is how do flames interact with and induce flow fields? Just because of the strong density jump across the flames really change the flow field both after the flame, but also in front of the flame. Obviously, subsonic flows, the flow in front of the flame can feel that flame, and they do things to react to it. So just quickly, though, I want to just introduce a couple definitions here. And so flashback and flame holding. So flashback is what I'm actually going to talk about. But that's the upstream propagation of a premixed flame into a region not designed for the flame to exist. And so notionally, this occurs when your laminar flame speed or your turbulent flame speed exceeds the local flow velocity. And so that sort of obvious sounding statement actually becomes really complicated because you have to ask yourself, well, let's just say it's the laminar flame speed. What laminar flame speed and what flow velocity? Because first of all, there is not one laminar flame speed, there's a whole continuum of laminar flame speeds because most laminar flames are what we call stretch sensitives. And so that means the flame speed changes with curvature. Particularly hydrogen flames, the flame speed can change a lot, like a factor of 5 or 6 by curvature. The second is what's the reference flow speed that it's propagating into. And that's not necessarily the approach flow because as I just mentioned, the flame changes what's in front of it. The flow field is subsonic, so the actual reference flow speed can be quite different. And that's what makes this problem so rich is we'll start by just assuming, well, laminar unstretched flame speed, reference approach flow velocity are our reference velocities, but then we'll add some more to it. With that said, and I think I should emphasize is that there's a difference between flashback, which is a common word, and the second word you'll see different words in the literature, and this is really more of an industry concept. It's in my textbook, but it hasn't really entered most other textbooks. And I've used the word flame holding, and I should emphasize that some people use the word flame holding to refer to flame stabilization, so don't get confused by that. But like if you take like industry, when they refer to flame holding, is what they mean is, let's suppose that I have a flame that flashes back, maybe during a transient. And then I return my conditions to steady state where a flame couldn't flash back, but will the flame stay anchored in the premixing passage? And the way that this is actually done in industry to test is that they will take a torch and they will actually manually introduce a flame into the premixing passage, turn it off, and say, does the flame get disgorged? Does it shoot downstream or does it stay upstream? And so, in fact, industry, this word flashback, industry doesn't care about flashback margins. People in industry care about flame holding margins because what they would say is, look, I can't have a design. Let's suppose I have a design that won't flash back, but there's some crazy transient in the system. You know, the electrical grid frequency burps, or there's some change in my fuel composition quickly, and somehow the flame can propagate upstream. As soon as I go back to my steady state, that flame better get shot right back downstream because otherwise it's just going to be sitting there cooking my hardware. So flame holding problem is actually really more of a blowout problem. But not a blowout from the main combustor, but a blowout from premixing hardware. And what makes this problem so interesting is it's got all these hysteretic elements. Is that, for example, a flame that might not hold in the wake of something under one condition, if it was hot already, could hold, and then the thermal feedback it can hold itself. So anyway, I just emphasize this, and I think, but just this general problem of flame holding, I think, is really understudied in the world. People spend more time on flashback, but really, again, what industry cares about at the end of the day is flame holding. What also makes this interesting is there is not just one mechanism in any real flow by which a flame can propagate upstream. It can flash back in the boundary layer, as you might expect, right? Obviously, in a boundary layer, the velocity has got to go to 0 at the wall. And so there will be a point where the flow speed is less than the nominal flame speed. The question is, can the flame exist at that point in the flow, or is it so close to the wall that the heat losses kill the flame? And that's really what controls whether flashback occurs in a boundary layer or not. Because again, there will always be a point in the flow where your velocity is low enough. And just to, let me just show you a video here. We don't like to see that. Well, I'll show you some stills, screenshots. The other thing that can happen is the flame can propagate in the core flow. So in other words, if the flame can find a place just in the bulk flow away from boundary layer where the velocity is lower, it can shoot upstream. Well, again, this one sounds kind of obvious, and no one would ever design a system where the flame could propagate into the core flow knowingly, right? Because you can say, all right, and frankly speaking, you know, if the flow is going 60 meters per second, not even a turbulent hydrogen flame propagates that fast. So, but what makes life interesting is as soon as you add swirl to a flow, there are additional physical processes whereby that you can have that flow that's shooting along at 60 meters per second, and the flame can actually trigger a phenomenon called vortex breakdown, where it can bring the flow in front of it to a screeching halt. Like I said, it's like Moses parting the waters in front of it. It can actually bring the flow to a screeching halt in front of it so that it can propagate into it. Really interesting. Or you can have a combustion instability. So during combustion instabilities, the whole flow is oscillating. And so let's suppose your nominal velocity is 60 meters per second, but it is not uncommon if you have a large instability for the flow, the velocity oscillations to reach 100%, which means there is a point in the cycle where it gets to 0 meters per second and a point in the cycle where it gets to 120. So the flow is sloshing back and forth and it can get pulled back. And as you might imagine, the significance of these different mechanisms, these are all different mechanisms, and they're going to have different sensitivities to fuel composition and operating conditions and fluid mechanics and so forth. And so just the basic things like scaling, like, you know, lots of times what people use in to understand, or at least a few years ago, to try to figure out, well, what's going to happen if I start adding hydrogen to natural gas is to use basic laminar unstretched flame speed considerations to scale. Well, if laminar unstretched flame speed is absolutely, this flame propagation in the core flow couldn't care less about the laminar unstretched. So you can match that. It's other parameters. It turns out it's the gas expansion ratio across the flame that matters for this second parameter. For flashback in the boundary layer, it's not laminar unstretched flame speed. It's really kind of a stretch sensitivity in a mixture and a flame thickness that matters. So anyway, and actually I have here these are a couple images. This is a flame flashing back in the core flow. This image right here is a flame flashing back in the boundary layer right there. And I'll show you those two in a minute. But let's just kind of start with classical treatment of boundary layer flashback. And so to do this, I'm going to make two really big assumptions. And one is I'm going to neglect the effect of heat release. And the way, it's not going to be explicit why I'm neglecting heat release, but the way implicitly I'm neglecting heat release is I'm going to assume I know the flow velocity profile. So I'm going to say, assume this flow velocity. But you might say, well, hold on, but won't the flame change that flow velocity? That's why I'm neglecting gas expansion. But we'll talk about what that does in a minute. And then the second thing is I'm going to neglect the effect of stretch. So this might be an image of what the flame might actually look like. It's, you know, it's going to be pushed away at these higher velocities, and then it might actually look something like this, and then it'll quench at some distance delta Q. But in reality, this point on the flame that's curved, it's going to be different than the laminar unstretched flame speed. But basically what will happen is the flashback occurs if the flame speed exceeds the flow velocity, you know, at some distance from the wall. So we'll call this delta Q, the quenching distance, if the velocity at y equals delta Q is equal to the flame speed. And this is the nomenclature from my textbook, but D denotes displacement speed. It's how fast the flame propagates with respect to the flow. and U denotes displacement speed with respect to the reactants. So if that confuses you, don't worry about it. It just turns out that when you start to really think about stretched flames, that definitions become important. But anyway, so the flame speed at that point. And so presumably, in sort of the classic way to do this, I'm just mirroring kind of a classic treatment, is that I'm going to expand the velocity in a Taylor series around its value at the wall. Its value at the wall is 0. So the velocity at y equals delta q will equal the velocity at y equals 0, which is 0 plus du dx, du dy times del q. And then I can, and that parameter is what the velocity is. And if I substitute it back into here, I get the condition that flashback will occur when the velocity gradient, which I've called GU, times that quenching distance divided by the flame speed is 1. Or I can call this a Karlovitz number right here. So if I assume that the quenching distance, I don't know why this is a Microsoft thing. If the quenching distance is basically equal to the flame thickness, which all indications seem to indicate it is, then I can define this Karlovitz number, which is velocity gradient times delta F over SD. And this actually works reasonably okay. So on the top right, this is data, measured data measuring critical velocity gradient. So basically what they would do is these are some pretty classic experiments where they would just drop flow velocity through a laminar burner until the flame flashed back, and then they'd calculate the velocity gradient, which was the y-axis, GU. Sorry, I'm using the mouse on my screen again. And this is equivalence ratio. So, and as you might expect, equivalence ratio of 1 requires the highest velocity gradient to keep it from flashing back. And then this is increasing reactant temperature, increasing TU, the U denotes reactant temperature, unburned temperature. So requires a higher gradient to keep the flame from flashing back. So, one of the beauties that we have today that they didn't have when they were making these measurements is that we've got detailed kinetics and great kinetic tools. So I just went in and I extracted their numbers, ran them through Chemkin. I calculated an unstretched flame speed. I calculated a flame thickness. And I threw all that data on this plot right here. And here is that Karlovitz number, equivalence ratio, and here's all that data, the solid lines. And you can see it actually, it's not perfect, but it collapses a lot of the data. Turns out that it's a Karlovitz number of 0.5 rather than 1, but it does reasonably well. The open symbols I've added propane air as well. And you can see it's actually, you see an equivalence ratio sensitivity there. But, in terms of kind of 0th order correlations, it works reasonably well. But in terms of, but you can also see that for quantitative predictions, it doesn't work. In fact, there's scatter, it's off by a factor of 2. There's some additional equivalence ratio sensitivities. So what's going on there? Well, let's first talk about a little bit about combustion aerodynamics now. And so as soon as a flat flame, if you have flow approaching a flat flame, the flame doesn't change the velocity profile. But as soon as you start curving a flame, you change the velocity in front of it. How many of you are familiar with something called the Darius-Landau instability? Okay. So the Darius-Landau instability is kind of a really interesting instability that you get in premix flames, whereby it's not possible to have a flat flame. You'd say, assume a flat flame, but the flame says, I don't want to be flat, because that configuration, it turns out, is unstable. And the reason for instability is very simple. And here I have a simple calculation, a simple plot. Imagine that I were to take a flame and I were to wrinkle it, okay? I have some approach flow velocity upstream of the flame. And then these velocity vectors show what the velocity vectors are doing as you approach the flame. The lines denote pressure isocontours. And remember, momentum equation, flow acceleration is proportional to grad p. So the flow is accelerating normal to those. So the acceleration of the flow is happening in the direction normal to these pressure contours. And so you can see that the flow is converging in, it's getting turned in. And these pressure contours are light, which means the pressure drops relative to the approach flow pressure. And over here, this is where it is, this is convex, I forgot. Convex to the reactants or concave? This is convex, this is concave, right? Convex, and you see the pressure is higher than the ambient pressure. And you see the flow diverging. So there's a couple of things going on here. So the pressure is, and oh, by the way, I also down here, I've made a plot. So here's that flame that I've curved. This dashed line, if I were to plot the pressure and the velocity, whoops, the pressure and the velocity along that line, the pressure upstream of the flame does that, and you can also see that here, that the pressure is above. The pressure rises, and the pressure and the velocity drops. Well, okay, the velocity and the pressure and velocity go together, right? So basically, the pressure is rising, so the flame is actually back pressuring the flow. You get an adverse pressure gradient. And because the pressure is rising, the flow is decelerating, right? Force equals mass times acceleration. So the pressure is rising, it's slowing the flow down, and the flame is back pressuring it. And so what that means is, and this is the mechanism for the Darius-Landau instability, if this flame speed is constant, and if the flame was flat, if the approach flow velocity matches the flame speed, then this flame's just going to park there. But now you have a configuration where the flame speed is greater than the local flow speed here. So this bulge that I just created on the flame is going to grow. The flame's going to move in this direction because the flame is back pressuring the flow, flow's slowing down, means the flame speed's higher than the flow speed, the flame's moving upstream. The opposite happens on the concave part, right? Here the flow is accelerating, the pressure is dropping, which is going to push the flame, which means the flow speed is higher than the flame speed, it's going to push that bulge to the right. So Darius-Landau instability just means if you create a wrinkle on the flame, that wrinkle is going to grow just due to the combined action of gas expansion and flame curvature. And it is the gas expansion that causes this back pressuring. If there was no density jump across the flame, this wouldn't happen. But what you can see from this example is that going back to this point I made earlier on what's the reference flow speed and burning velocity, is that the flow that the flame sees is not the nominal upstream flow in the absence of the flame. The flame changes what it's reacting to. It's like the flame is a magic power. Like if I had this magic power, I could swim in a stream. You know, if you're seeing these images of Yosemite and these boiling streams, it's almost like if I could swim in the stream and make the water in front of me slow down in front of me, because I can't swim very fast. Right? So instead of me getting shot downstream, if I could swim upstream. This is what flames do, and it's because they have gas expansion. The flames actually change the velocity right in front of them. Now, obviously, mass is conserved, which means the flow is going to have to do something else, accelerate, but right in front of the flame slows it down, which creates a lot of really interesting things. So what that does in the context of, well, there's a bunch of points I want to make, but let me just jump into this one then. One of the things that does is, if I jump ahead here, is flames flashing back in boundary layers, they back pressure the flow in front of them. And what do you all know from fluid mechanics class? What do boundary layers not like? Boundary layers do not like adverse pressure gradients. When you give a boundary layer an adverse pressure gradient, you can make the boundary layer separate, right? And that's exactly what's happening in these images here. Really cool images from these papers here, where here's a wall, here are streamlines, here's the flame, here's the flow, and you can see the flow getting out of the way of the flame. So it's slowing down. That part is actually, the boundary layer is separated. The flow is actually going backwards. So this boundary layer is actually pulling the flame into it. The flow velocity right upstream of the flame is actually going backwards. It's pulling the flame upstream. So this is an example of this flame aerodynamics, whereby the flame is decelerating the flow in front of it, which is a consideration that's not built into those classical scalings. Let me back up now. So That's this point right here. So the fact that flames, that you get this coupled effect of flame curvature and gas expansion means that whenever you have a flame in a boundary layer, and if that flame is curved, which it always will be because the flow velocity is not constant, which causes, so, you know, if you just think about combustion one, you know, sine theta equals SL over U, whatever, if U is changing, that's going to cause theta to change. So whenever you have curvature plus the effect of gas expansion, adverse pressure gradients lead to separations. Now, one of the things this is really important is that gas expansion ratios are really important for flame aerodynamics. So let me give you an example. Atmospheric pressure combustion with ambient temperature reactants, like if any of you are doing experiments in your lab, reactants at 300 K. Well, if reactants at 300 K, let's say you have a flame temperature of 1800 K, you have a gas expansion ratio of 6, okay? So if you're just, and these are pretty typical numbers for kind of lab scale experiments at atmospheric pressure and with ambient temperature. So gas expands by a factor of 6. This effect is really, really powerful. Think about now aircraft engines where the air is not at 300 K anymore, but it's at 900 K, all right? So now the flame let's say the flame temperature is 1800 K. So 1800 K divided by 900 K is 2. Gas expansion ratio is about 2 in that device. And so you can have very, very, very different controlling flame air. The influence of the flame on the approach flow can be profoundly different depending upon that ratio of reactant temperature. And it's hard to change flame temperature by too much. But you can change reactant temperature by a lot. And so where this really shows up is in things like augmenters, you know, used on the back end of jet engines to get more thrust, is because the air is really hot. You can have gas expansion ratios of more like 1.5. And so, you know, just fundamentally different sort of flame fluid mechanic interactions with those types of applications than else. I'm going to now, just to keep us on track, I'm not going to go through all this stuff, but I think I'm going to give you one more example about swirl flows, again, how this flame aerodynamics matters. And I'm going to use that in the application of how flames can flash back in the core flow. In particular, I want to talk about swirling flows, because like I said, you might say, you know, that problem's kind of trivial. Flame flash back in the core flow. You know, why would you ever design a flow where the velocity is less than the flame speed? And you wouldn't. But when you swirl the flow, you get some interesting fluid mechanic instabilities. How many of you are familiar with the phenomenon of vortex breakdown in swirl flows? Okay, good. So the basic idea is, imagine a pipe, flows spinning. We can define a swirl number, what I called S. And the swirl number, there's different definitions, but basically think about it as the ratio of azimuthal velocity to axial velocity. Mother Nature has this really cool, this is why the combination of fluid mechanics and combustion is so interesting, is that when the swirl number exceeds a certain critical value, you get a phenomenon called vortex breakdown. So let's say you got a pipe, the flow is moving 100 miles an hour through it. Once you get a swirl number of, let's just say 0.8, vortex breakdown happens. What happens is you will actually get a recirculating pocket of fluid in the center of the flow. There's no flow separation. There's no, you know, but just you get this, the flow, basically you get an interior, what we call an interior stagnation point. So just to illustrate that here, I have this sketch. These are streamlines. I haven't drawn the azimuthal velocity component. I'll tell you in a minute why I've drawn this backward-facing step. But notice this is a stagnation point. So the flow velocity is, like I said, it's zooming along at 100 miles an hour, and it comes to a screeching stop. It actually stops, and you get this recirculating cell of fluid, and then the rest of the fluid, obviously mass is conserved, has to accelerate around it. That's vortex breakdown. And I won't get into the details of why, but it's just it's a fluid mechanic instability where you get interaction of different vorticity terms. But it's kind of cool, though, because you can actually create this low velocity region in the interior of a fluid without any hardware, without forcing flow separation. We'll talk about this tomorrow when we talk about flame stabilization, but normally to stabilize flames, you have to force some flow separation to get a low velocity region, otherwise the flame will just go flying out the back end of your combustor. But by swirling the flow, you can do this, which is why essentially every fielded combustion system in the world today uses swirl to help stabilize the system, to help stabilize the flame. That bottom right image is a really pretty little image where they put some seed right in the very dead center of the flow, and you can see it hit that stagnation point, and then you can kind of visualize that smoke getting entrained into that cell, and so forth. And these are just some other images of vortex breakdown. Let's just jumping through this though. Let me just tell you why I drew this backward-facing step here. It turns out that if you have a straight pipe and it has swirl, vortex breakdown can happen anywhere along this pipe. It could be here, it could be here, it could be here. And in fact, what will happen is if you did that experiment, you would see the vortex breakdown region kind of meandering back and forth and so forth. Turns out, though, that the mechanism for vortex breakdown is really sensitive to the flow deceleration or adverse pressure gradients. And so by putting a little bit of a step in the wall, I create the flow, the base flow slows down because the area increases. And for flows to slow down, the pressure has to rise. And that actually trips vortex breakdown, so it kind of locks the vortex breakdown point right there. It doesn't move. And so then you can stare at it and throw lasers at it and things like that. Okay, so vortex breakdown is sensitive to adverse pressure gradients. We just talked about that. And what do we say flames do? They back pressure flows. So now let's imagine a combination of flames and vortex breakdown. So I have a little, so TUM guy, I know TUM one person. This is work from TUM, from Saddlemeyer's group, who kind of discovered this mechanism called combustion-induced vortex breakdown, is that you've got this vortex breakdown to stabilize the flow, to slow it down. You've got this curved flame in front of it, and what the flame can actually do is it can trip vortex breakdown in front of it. So the flow's coming 60 miles an hour at the flame, and the flame says, please, it stops the flow in front of it. And so the flame can move forward, causes vortex breakdown to move upstream, flame moves upstream, trips. And so the flame can shoot upstream in a swirl, in the core of a swirling flow, even though the nominal flow, in the absence of the flame, is moving at a speed much higher than the flame could ever propagate. Let me just jump back here. So anyway, just lots of interesting applications of how curvature and gas expansion can materially change flow. So just to summarize, again, we talked about flame stability, the Darius-Landau instability. And this is really the only thing where people talk about in existing textbooks, but also boundary layers, and now I just gave you an example of swirl flows. There's actually a third example that's pretty interesting that shows up in non-premixed systems. Non-premixed flames, whenever you lift a flame from if you have a fuel, an oxidizer, as soon as the flame lifts, you get a certain amount of premixing, and you get what's called a triple flame. Well, where and how the flame sits is also profoundly influenced by this phenomenon. So, anybody studying triple flames or tribrachial flames? Okay. So, all right. So that's all I'm going to say about flashback and flame aerodynamics. It was more just to kind of whet your appetite. There's in my combustion textbook, I have quite a bit of material on this. But I now want to talk about flame stabilization, which is kind of a related phenomenon. And so jumping ahead, but the whole idea here is, well, and there's a lot more here that I'm going to get into, by the way, but I put a lot of extra material just based upon if there were specific questions. How do flames stabilize, right? How is it that, like I said, we're going to talk in this class about steady flowing applications, so presumably the flame parks itself at a given position, doesn't move. Well, what makes a flame decide to park itself at a steady position and not move? What keeps it from flashing back, shooting upstream, or blowing off, moving downstream? To have flame stabilization work, you got to have a point where the local flame speed and the flow speed match, right? So the flame speed's got to match the flow speed. That's typically found in two places, regions where you have low flow velocity. And so one way that can happen is in what we would call an aerodynamically decelerated region, i.e. flows with swirl. VBB stands for vortex breakdown bubble. Sorry for the undefined acronym. And I have an example here, right in this image right here. So you got a swirling flow, and the flame is just floating out in space. And the reason it can float out in space is because I've got enough swirl in the flow that the flow decelerates, you get vortex breakdown, and the flame can find a spot where it matches the flow speed. That's one way. The other way is in a region of high shear. So if you're in a region of high shear, it's basically what I mean is a point where the flow velocity basically goes to zero, nearly goes to zero, near combustor walls. And so, again, sorry for not defining the acronym. ISL denotes inner shear layer, OSL denotes outer shear layer, but the general idea is flames can sit in shear layers. So even though the core flow velocity in the bulk flow speed might be very high, at some point it's going to go to zero, and the flame can potentially park there. But because it's in that region of high shear, for those of you who are familiar with the concept of flame stretch, shear in flows modifies flame's internal structure and changes their burning rates. And if the shear is too high, it can actually extinguish the flame. But, just a reminder that, okay, so this, again, classic treatment of flame stabilization just to get started. So that you've probably seen pictures like this before, is that imagine I have this velocity profile, this flame speed profile. So I have some quenching distance where the flame can't exist. So the flame speed is zero here, and then I'll just assume it pops up to some flame speed there. And then I have these velocity profiles. This is velocity profile C, B, and A. So this is the velocity as a function of distance from the wall. So the velocity is going to zero at the wall. So configuration C, there are points where the flame speed is greater than the flow speed. That flame's going to move upstream, right? Potentially start to flashback. Configuration A, the flame speed is everywhere less than the flow speed, and that flame is going to move downstream. I would say it's going to blow off, but before I say blow off, it's going to move downstream. As it moves downstream, it cannot find a point where it matches the flow speed, it will blow off. In the same way, configuration C, I would say it would flash back, but again, it's going to move upstream, and if something doesn't change, it will continue moving upstream. And so what's special about configuration B is there is one spot where the flame speed and the flow speed match, and the flame parks right there. And then, even though the flame speed is where the flow velocity is less, the flame is quenched. And even though the flow velocity is greater than that at other points, that's no problem. The flame can anchor itself, and the other points, it just swings to an angle where sine theta equals SL over U. So again, it's kind of like, I always like to use an illustration of me swimming in a river. The river's going a lot faster than I am. I can't swim upstream, but if I can anchor myself, if I tie a rope around my waist, tie it to a stake on the shore, hammer the shore in, my body will swing to an angle where I'm swimming in the river, where my swimming speed divided by flow velocity equals sine theta. But I gotta have that stabilization point where they match. Critical. But what this also suggests is that you're like, wow, stable flames must be really rare because they've got to exactly look like configuration B. If they look like anything else, it's going to flash back and blow off. But in reality, flames have self-stabilizing mechanisms such that if they start to flash back, what can happen is that heat losses can increase and they slow down. Or if it starts to blow off, other things might happen. And so in reality, usually what oftentimes happens is the flame adjusts its position slightly as we're changing temperature, fuel composition, or flow velocity. It might move a little off a burner lip or move down, but it'll find that balancing point. But I guess just the key point, though, is that stabilization point and then the spreading of the flame from that stabilization point are profoundly different problems. Totally different problems. And if there is no stabilization point, that flame will blow off. In our PhD quals, I'm always amazed at how people don't figure that out, as they want to assume sine theta equals SL over U. Sine theta equals SL over U is fine if you have a stabilization point where SL equals U at some point. But if SL never equals U, there is no sine theta equals SL over U. Flame's gone. It's out of here. Just like I'm shot downstream if I'm trying to swim in it, right? Okay, so that's just one thing to say. In reality, complex flows, like we find in reality, there's not one stabilization point, but there's actually many stabilization points. And in fact, just to illustrate, these are some images. It's probably a little bit easier if we look at this image. So a very common configuration, almost a universal configuration in real combustion systems is this, what I've shown. A, B, C, and D, it's the same geometry, but imagine a nozzle whose area increases, and then there's a center body in the middle, all right? Really common, and I can break this down for you. So here I have this. This is a premixing passage. This is a smaller diameter than that because I want the flow velocity to be really high because I don't want the flame to flash back to. This is my premixing passage, okay? Premixing passage, I want high velocity, I don't want flashback. And then this is your combustor diameter. This center body is, the reason I have that is this is really common in combustion systems because, for example, maybe you need pilot flows, or if somebody was talking to me about water injection, or if you need dual fuel where you can change it, such that you have a way to pipe fuel in that you can spray in here. The other reason we oftentimes put these center bodies in is it's really hard to have a clean velocity in the middle of a swirling flow. If you're not careful, a swirling flow can give you reverse flow right here, right in the center. So the way to deal with that is just put a center body in and it washes that out. But what that means then is, now this is the ISL, OSL, is you imagine this is a circle. So you have the center body and there's an inner shear layer. So there's the velocity goes to 0 at this wall, ISL. And then there is an outer shear layer, which is that wall. That's the OSL. So this configuration, and then the flow is swirling, presumably. And so configuration A would be a configuration where the flame is what we call aerodynamically stabilized. It found a spot where the flow decelerated due to that vortex breakdown bubble, that was the VBB acronym, matched. Configuration B is a configuration where the flame actually has found two stabilization locations. It's sitting in the middle. You notice that it's coming, well, let's start with the outer shear layer. It's sitting in the outer shear layer, and then it wraps back around. If there was no inner shear, if there was no vortex breakdown bubble, this flame would just have a kind of a classic, just kind of a big bold U.S. shape here. Configuration C is where the flame is sitting in the inner shear layer. Configuration D is where it's sitting in the inner shear layer and outer shear layer. 4 different families of possible flame shapes. We see them in all. Here they are. These are line of sight chemiluminescence. So, like for example, bottom left is inner shear layer, bottom right is inner and outer shear layer. So what we have here is a bunch of problems where there's lots of different flame stabilization locations, and where the flame sits is going to be a function of operating conditions, fuel composition, and so forth. So what oftentimes happens in reality is if I've got a really fast flame and a low flow velocity, I start at configuration D. The flame parks itself in the inner and outer shear layer. The flame's relatively short because it's spreading from 2 angles to consume all the reactants. The reactants are coming up. But then what oftentimes happens is that as I increase the flow velocity, it turns out that the shear layers have different thicknesses in those inner and outer shear layer due to swirl. The presence of swirl causes that outer shear layer usually to be thinner and there to be more shear, less friendly for flames. So what will oftentimes happen is the flame essentially locally blows out. It doesn't completely blow out, but it can no longer survive in that outer shear layer. So what will happen is I'll be maybe adjusting velocity. I'm just gradually increasing velocity, and all of a sudden, bam, bifurcation. Flame jumps from shape D to C. Flame doubles in length instantaneously. Yeah. And so that's that. And where that's going to, remember my comments before about pressure, is where flames can survive changing with pressure, is where that bifurcation will occur will be very different at 1 bar than at 10 bar, just because the flame can hang on longer at 10 bar. Sometimes it's a little harder to do. Configuration B is a little harder to find, but if you make your center body, if you don't have a center body or you make it really, really thin, then you can also make D jump to B. And then if you keep dropping it, the flame may say, I can't sit in any of these shear layers. it starts to move downstream, but it doesn't blow out because there's vortex breakdown. And you'll see configuration A, and then it blows out. So you can actually see the phenomenon of blowout is actually usually not just a single, the flame's not letting go. There's 3 distinct bifurcations that happens along the way. And as I'm changing ambient conditions and power setting and hydrogen and all this stuff, where it's going to be is going to be different for each configuration. And each one of those things, and we'll talk about this later, but for example, combustion instability limits. Combustion instability conditions are really sensitive to how long flames are. Configuration C and configuration D will be unstable under completely different operating conditions. And it jumps, right? Those flame shapes jump. All right, well, we have sat here for long enough. I think I'm going to stop for the day. Does anyone have any questions before I conclude?